Okay, so we're going to do a layout for this circuit here, and I've hand drawn this, and we're going to do something similar for the homework as well. But we're going to go through this first a little bit to talk a little bit about what this is and some kind of different ways that we're going to be able to use cadence. So first off, let me say that this is a very crappy audio amplifier. So we have an input here on the left hand side, and this wouldn't even be stereo, and it's really crappy quality. Let me just put it that way. So we have an input here, and it's going into the op amp, and then we have an output over here, and then we have these right here are power supplies for the op amp. And then we of course have all the other components here. So let me first talk a little bit about here. If you look at, here I'll highlight it in a different color, these two resistors here that are tied into this negative terminal, there's a formula, which you'll learn more in detail later on, that you can determine the gain of this amplifier, basically how much it's multiplying the input by. And I've fixed the gain at this point, and the gain here is 1 plus 10 kiloohms over 1 kiloohm. So you could change these two resistors to change the gain. Like if I put a 20 kiloohm in there, well then I just put 20 kiloohms here. If I change this to a 5, well I'd change this 1 to a 5 then. Now, that gives me a gain of 11. So that's what this circuit is doing. It's amplifying. So honestly, it's a very basic circuit, but the principle or the concept behind it is the same way if you have a volume control on a headset or cell phone or anything like that. It's doing some kind of amplification of the audio signal. Now, it's not going to be like this. It's usually a digital signal and lots of other things going on. But that's beyond the point. This would work. Now, let's talk about these little bar symbols here. This is something in cadence so that you can kind of clean up your diagram. This basically V plus, here I'll even highlight it in a different color right now. That V plus is basically connected over here. So there is a connection. It's just not drawn. So that V bar actually makes that connection. And this can help because imagine if you had 20 chips and they all needed a 12-volt power supply on them. Instead of having to wire them all up to a 12-volt battery, you can just say V plus and have one set up at 12 volt and then put this V plus with this bar thing for all of those power supplies. Similarly, if I look at let's use green here. If I look at this one here, this V minus, that's connected to this V minus. So there's actually a physical wire connection between those 2 points, even though we don't see it. And again, it makes it so that we don't have wires sitting on top of each other all the way. It just keeps the diagram a little bit cleaner. And we're going to use that there. Now, the other thing I want to point out is a couple of the elements here and talk about them a little bit. So let's look at this capacitor and this resistor first. Well, this 4.7 microfarad capacitor is blocking DC voltage. Now, when you get into your circuit analysis classes, you'll learn in more detail on why that's blocking DC voltage. I'll give you a little hint on there. You don't need to know this for this class. There's something for a capacitor that's called an impedance, which is it's like resistance. The impedance for a capacitor is 1 over j omega c. And so this is frequency, and this j is actually the imaginary number. Square root of -1. And those of you who've learned about imaginary numbers, you might say, wait a minute, we use I for imaginary. Well, not in electrical engineering, we use J because I is for current. So we definitely use J for the imaginary number, and C is the capacitance. And so without going into too much detail, if you have a low frequency, which technically the frequency of DC is 0, but if you have a low frequency and actually technically a DC signal probably does have some frequency because if there's any kind of ripple voltage, but getting ahead of myself. Basically what will happen is that will block the DC voltage from going through because this number will become a huge number, a big number. Now, what will end up happening though is an AC signal will actually pass through here. So an AC signal, like an audio signal, will still pass through. And when we say AC, don't think of AC as just power. I mean, that's what we often think of as the 110 coming out of the walls. But AC signal is anything that goes up and down. And if you've ever seen kind of those little visualizations of an audio signal, it's kind of going up and down. It's actually like a bunch of sine waves and stuff. And so that's an AC signal still. So that AC signal will be able to get through that capacitor to the output here. Now what about this 10 ohm resistor? Well, this is for what's called impedance matching. And for anyone who's ever played with audio before, knows that for maximum power transfer, you have to match the impedance of the speakers with the output impedance of the amplifier. And so in this case, I dropped a 10 ohm resistor in there because most speakers that like headsets have like maybe an 8 ohm impedance. I mean, there's lots of, you can have 4 ohm, 16 ohm, but like a common one for earbuds, for instance, is 8 ohms. Now, you might say, why didn't I put an 8 ohm resistor in there? I'm not going to go into that. Put a 10 ohm in there. All right, then there's two other things that we should look at here that before we get into how we're going to do this layout. We've got this 10 microfarad capacitor here and this 10 microfarad capacitor here. These are capacitors that are basically will be placed close to the chip in order to aid in power. So let me just explain real briefly why we want those there. So we have this AC signal. It's going to go up and down, up and down, up and down. You know, it's not going to necessarily look like that, but it's just going to go up and down and up and down. And so this op amp has to go from like this high positive voltage all the way to this low negative voltage up to this high positive voltage. And so what it needs is it needs energy, it needs charge to be able to do that quickly. You know, because if we're talking about particular frequency, and so what that does is if we put these kind of close to the chip, it kind of is like a little storage tank of energy. So we can store some charge for the op amp to steal away from it, and then it will get recharged by the power supply that might be on the other side of the board, is where maybe the battery is located. And so this allows it helps with making sure that the chip sees what we call a clean power supply. It helps with preventing noise on the power lines. You can actually pick up audio noise on your power lines. Anytime you have a wire, that's an antenna. So there's all sorts of things. And so there's a lot of things those capacitors can help with. So you're going to always see that when you are looking at chips as you move throughout your career here. Now, when you get into circuit analysis, we often ignore those capacitors because we're just looking at the actual analysis of what's going on in this op-amp circuit, and we just assume the power supplies, do everything we need them to do. But in practice, we have to put those back in when we're building a real circuit in order to get good power, good clean power for our chips. So, all right, so what we need to do then is we're going to need to take this and put it into cadence, and we're going to need to replace these batteries here with connectors. I don't want to put a battery here in my drawing, so I'm going to be removing those. All right, so let me bring up Capture CIS here, and I believe I can just use a new design here. But to be safe here, I'm going to just do new projects. New project versus new design. New design is basically where you're doing like a schematic, which really is all we're doing here. New project means that we are also going to want to be able to simulate it. Now, we're probably not going to simulate this, but let's go ahead and just do new project. Let's do PSpice, analog, or mixed A and D. And we could do a schematic here, since all we're doing is a schematic, and that would be fine. But let's go ahead and make sure that we can do a simulation if we want to. When you're doing a layout, though, in industry, they often use this schematic option so that someone doesn't try and simulate this design. But we're going to go and use the analog mixed A and D. So let me put this in here. I'm going to create a directory and do layout 1. And I've probably already got it here, so I've probably already used this directory before, but that's fine. I'm just going to call this layout 1. Yeah, it says, oh, you've already done this. Yeah, we'll replace the project. Okay, so I'm going to go here, double click to bring up my schematic. Oh, wait. It didn't create a new one, it just opened my other one. Crap, that's not what I wanted to do. And you can see it's actually kind of the same project here. Okay, let me close this one here. Let me close this. Let me do new project. And let's just do layout 10-8-2021. Definitely know there wouldn't be one for that. Okay, so we'll do that, create a blanks thing. Okay, here we go. Blanked diagram here. Now, let me move this a little bit over so I make sure to bring, so that you can see all of the different things I'm going to do. So I'm going to bring my parts over here, and I'm going to remove all of my libraries here for now, just so that I can show you which ones we're going to use. Yeah, I can't remove the design cache, fine, whatever. Okay, so I'm going to add in libraries here. The reason these look different than ones that you're used to look as far as this icon is I have, again, a newer version of Cadence installed on my system. I'm still using the old version, though, to make these videos. Alright, so what ones do we need here? Well, I don't think we need the source, but I always like to include it. We're going to need the op-amp. We are going to need analog. Oops, went way too far. Okay. One I also like to include is breakout when I'm doing layouts. So breakout is a very good one for layouts. And so I'm going to open those. I'm going to add 2 more. I'm going to go up one directory, and I'm going to add capsim and connector. Open those up. Okay, so let's look at the connector, just scrolling through these. You can see, as the name would suggest, it's got all sorts of different types of connectors on here, and it's got some just generic connectors as well, which, you know, basically, like if you look here, connector 4, that's just some generic connector that you might not know. Instead of trying to find a specific part that represents that precise connector, you can just say, oh, well, I'm just using one that has the generic connector on that. So, all right. Well, let's go ahead and start building this here. So I have 3 resistors, so I'm going to double click on my resistor and put 3 resistors down. I'm just double checking to make sure. I got 4 resistors. So let's make sure to put all 4 down. Let me zoom in a tiny bit. Escape. And now I have capacitors. Now, one thing I didn't maybe emphasize here, and let's emphasize it, is the way I've drawn these capacitors. There's 2 ways you can draw capacitors. One way is that you draw them like this. And these are typically for non-polarized capacitors. Now, and I exaggerated, this is a horizontal line, and then there's this curve here. These are polarized caps, often referred to as electrolytics, but those aren't the only type. That's just one type of polarized capacitor. So non-polarized, it does not matter what orientation you put the capacitor in. A polarized capacitor, it matters how you put it in, like whether you have it in one direction or if you rotate it 180 degrees. So, polarized capacitor, this has a plus and a minus. So the horizontal, or the straight piece, the non-curved piece is always the plus, and the curved piece is always the minus. So if I go back here, this is always the plus, and then this would be the minus. This would be the plus, minus, plus, minus. Okay, so I have 3 of those electrolytic capacitors. Now, in Cadence, it doesn't actually show the curve, but you can see there's that plus. And so I'm going to have the plus going in the direction. So one of them is facing that way, and then 2 of them were off over here, but I'm actually, because of the way I have this sketched right now, I'm going to put them in the bottom corner here. And then we also have an LM741. So if I go to the op amp and just type in LM741, it brings it up. Now, one thing you have to be careful when using it is notice where the negative and the plus is here. And then look at my diagram here where the plus and the negative is. So I want to flip this. So I'm going to select this component, and then I'm going to mirror this vertically. Okay. Now I'm going to go ahead and add a couple grounds in here. And then I'm not actually going to add the power supplies in. We'll see what I'm going to do here in a second, but I will go ahead and add these V bars in. So over here, there's this place power. So I'm going to do this, and I'm going to scroll down, and there's this VCC bar, and I'm going to put 2 of those in here. And I'm going to simply rename one to be V plus, and I'm going to rename the other one to be V minus. Now I'm going to select it. I'm going to do Control C to copy, and then Control V to paste it. And so you can see I've got one up here. And it's the V minus, so I'm going to put it up by the V minus. And I'm going to do the same thing here. Select the V plus, copy and paste. I'm going to put it down here. And then I'm going to rotate it. Now I am going to go ahead and wire up everything. I know I don't have my batteries in. We'll take care of that in a second. And hopefully you pause the video and sketch the circuit down. I just remember what it looks like. Whoops. I forgot to change some values here. This is 10 kilo ohms. This is 10. This is 4.7 microfarads, so 4.7 U, and these are both 10 microfarads, 10 U and 10 U. And then these capacitors are also both connected to ground, and these are connected here. Okay, so I know that here I'm going to put some text in here, place text here. I know that I've got 5 volts, and I know that that's what this is supposed to be. I'll put it there here, and I'll just put here minus 5 volts. Edit that. So I know that's what those are supposed to be. But I don't have any power supply there yet. We are going to take care of that, because how we would get power into this is we'd have to use a connector. Okay, so that's what the next thing we're going to do. And then we also have here, now I'm not going to, here I'm going to put a weird wire here. I'm just going to leave a wire and then just kind of let it go out to nothing. And I'm going to do a couple other things here on this. So we wrote in text there, but then remember this net alias that we had talked about. Well, I'm going to do that again. And I'm going to label some things here. Well, we had the input. Now when you put a net alias, you can't just randomly put it down somewhere. You see, it's not letting me put it down. You have to put it on a wire. And so you can see, oh, okay, I'm on a wire, so I can put it down there. So I've labeled that wire the input. So what we're doing is, and let me show you here. See, if I hover on this wire, that wire's name is N00362, which is incredibly descriptive. And so what you can do, though, is you can make these more descriptives, these wires. And so instead of it being that N number, 00362, I can put it here, and if I spelled output correctly, I now have relabeled that wire to output. and this wire is relabeled to input. And this one is labeled 0, which I'm fine with that. That's referring to ground. If you wanted to, you could call it ground if that's what you really wanted to do. But then I'm also going to put a alias and say I don't know if it lets me do. Yeah, I think it does. Plus, I'm going to do plus 5 volts. And I'm going to attach it to this wire. Oh, I'm going to attach it to the actual positive 5 volts. And then I'll attach it to the negative one as well, because you can always just rename them by double-clicking them. So I've labeled some things here. Now, if I hover on this little wire here, you can see the name of it is V+. So it's going all the way. Wait, I think that was because I was trying to hover on that wire. Yeah, the name here of that wire is V+ because that wire is getting connected back to here. Okay? So, we have some of these nice little labelings that we can go on here. Now, we need to have connectors here. Now, we're not using any fancy connectors. We're going to use basically what our standard headers. And as far as what I mean by standard headers here, I don't even know if I have a Chrome open here. I do. Here's a Chrome announcement page there. So, female 4-pin header. So this is a 4-pin header, which is what we're going to use. And these are very convenient because you can plug breadboard wires into them, things of that nature. They're great for prototyping. For an actual production thing, they're terrible because they're not secure connections. But for now, we're going to use that. When we get into a later design, we'll use better connectors like a USB-A connector or something of that nature to actually, I mean, you wouldn't want to use a USB in this case, but we will use a USB in some cases. And I just realized, did I get the voltage wrong? I did get the voltage wrong. You guys have all been probably saying is, why is he putting 5 volts there? It was 12 volts. So let me fix those. Okay, so those are all fixed now. So let's do a connector here. Now there's two things. We could go connector, and now I just know these because I've used them quite a bit. If you go to CON, these are just generic connectors. Connector 4. Or you can do breakout, because breakout also has different types of just symbols. These don't have any kind of, they don't necessarily have SPICE models associated with them, but you can see, well, here's some for like transformers and stuff, and then, so there's different ones you can use in the breakout as well. But in this case, the other thing you can use in it, I think, is that, yeah, they also have header, like header 4, which looks a little bit different than connector 4, but it doesn't really matter. So in this here, let's just do the connector, yeah, connector 4, con 4. And so I'm going to use a 4-pin connector for everything, not because I'm going to use all the pins. You don't always use all the pins on a 4-pin connector, but because that's what I have available to me. Now, like for instance, a USB connector has 4 pins and not all 4 pins are used. But you don't always have all pins used. Here, let me see if I can give you an example real quickly. Yeah. So here's a VGA connector. And while technically, Well, actually, no, technically all pins aren't being used. So this is an old style monitor connector, right? Red, blue, but look, NC, 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 those stands for no connections. And then a bunch of them are tied to ground. Now there's a reason for that, but won't go into it. Then you have the horizontal sync, vertical sync, and then red, green, and blue. So very basic type of connector, but you can see not all the pins are used. But it was considered to be a standard type of connector, so let's use it because it had the right number of pins and it was a standard connector. So that's why we're going to use this 4-pin connector. Not 40. 4. So I'm going to put one here, and I'm going to just put another one here. And now they're labeled J1 and J2. Now I'm going to put some text in here, and I'm going to do 12 volt, and then I'm going to do Control Enter to start a new line, do a couple spaces, ground, another that, ground, minus 12 volt. And what I'm going to do is I'm going to place that right next to the J1. Now this text is really just comments for me, so I know what's going on, and I spelled volt out here and I did it V here. It doesn't really matter. Okay, so what do I want to do here? Well, that tells me how to run these connectors. Okay, well, pin 1 is 12 volts, so I would run this to here. And then ground, well, I'll tie those two ground pins together, and then connect them here. Now, as a side note, this ground is now also connected to the ground over here and to this ground. So I don't have to like connect this all the way over to here. Like once you connect the ground together, they're all the same ground. And then I will do the 12 volt, and I'm going to do the 12 volt by wiring it just so that for me it will help my eyes. And make sure that you don't click here because I don't want to make a connection there. Like that. Actually, I don't like that there, so I'm going to move this down a little bit. There we go. And so we can see here there's no connection here because there's no pink dot. So they're just laying on top of each other. So now I have a connector that and I can move my text box a little bit. I have a connector that has my things ready for connecting things up to. All right, now the next connector. Let's talk about that one here. Well, input and then output I need on it. Now you might say, why am I also putting ground on that? Because like, why would I need to have ground on there too? Because I already have ground over here. Well, we have to think about the fact that in reality, when we're connecting things up, you're going to have lots of ground connections you want floating all over the place. Because if you were connecting an earbud, an audio signal up to the input, the audio signal would have the audio input and ground that you would connect into the circuit. And then the output, your headset is, well, it's the output plus ground, because there's 2 wires, well, 3 wires for stereo, but there's 2 wires for a speaker. One is you can kind of think of as ground, and the other you can think of as the actual input. So I'm going to still have that like that. So the input, of course, I'm just going to be careful and connect up to my input. My output, of course, is going to get connected to my output. my grounds, I'm going to tie them together. And then I'm going to tie those together. And so I finally have my circuit diagram. Now I'm not done for getting things ready to do a layout. I have just built the schematic at this point. And based off of how much time I've taken for this and then the other introductory kind of review video, I don't know if we'll actually do the full layout this week, meaning I don't know if we'll actually get to doing the routing. I might punt that to next week, just because I want to make sure that you have time to watch this video maybe a couple times, and then you're going to want to try and recreate this. When you watch the video, I mean, it's good to watch it, but then you should always try and recreate whatever I'm doing in the video as well. And then, maybe we'll have a couple homework problems on this as well, to give you some practice. Because if we don't have this good and well understood, there's no way we'll be able to get it into the PCB editor to actually do a layout.